Welcome to an introduction to our course forecasting project. By the end of this lecture, you should be able to 1. Describe the aim of the forecasting project, namely, to practice applying principles of inductive logic to real-world problems, and 2. To state the expectations and general outline of the project. We can begin with some motivating questions, such as, when can we trust our intuitions? This is a deep and fascinating question, the answer to which many of us have wanted to know. We now actually have a compelling answer to this question, which comes from the behavioral economics literature over the past several decades, pioneered by scholars like Daniel Kahneman and Amos Tversky. The answer is that we can trust our intuitions just when they are produced by a process with the following properties: that it provides repeated feedback, and that the feedback is sufficiently clear that we know when our judgments have been wrong. I want you to pause and think for a moment about the implications of having such an answer to the question of when we can trust our intuitions. This is actually really rather remarkable. For concreteness, let's consider what sorts of judgments satisfy these conditions of being produced by repeated and clear feedback processes. The firefighter who, in a building, intuits that it may collapse may have a reliable intuition insofar as they have been in many buildings before and have observed those buildings fall, collapse, or not. The midwife who intuits that a child perhaps is not properly rotated can have a reliable intuition insofar as they have been at many birthings and gotten the feedback of whether indeed the child was well rotated or not repeatedly. Or the athlete who makes the snap judgment as to whether one approach or plan of attack will be successful or not, has again produced that intuition by a process of repeated and clear feedback, that is, over many games in which they experienced many failures. These are cases that have the potential to satisfy the conditions of having produced intuitions from processes of repeated and clear feedback. We can contrast these with the stockbroker who has an intuition about the motion of some market. Consider which factor here, which property is not satisfied. It's true that the stockbroker has a great deal of experience under their belt. However, the number of factors that go into the motion of a stock or the motion of a market are far too many, so that after the fact, even though they could observe that they were wrong, unfortunately, it is really not clear why they were wrong. Even though we might tell ourselves stories in such cases, the feedback that we get is deeply equivocal. Similarly, for the political pundit who tells stories about the tides and turns of the politics of the moment, who makes predictions about government behavior, about elections, about societal trends. These are again cases where a number of factors prevent even extraordinary experience being effective. All of them have to do with the lack of clarity of the feedback in that domain, that it is really not clear when and why we were wrong. And on this count, we can consider the philosopher, who uses their intuition to judge how, for example, space or time are necessarily organized, or make other intuitive judgments about how the world must be. Again, these intuitions, while they may have been made repeatedly, unfortunately provided no feedback because the philosopher was unable to observe when they were wrong in many of those cases. And in those cases, what we see is that wherever we're able to test those intuitions with time, that they're shown repeatedly to be really almost entirely unreliable unless they were produced by a process which satisfied these conditions. A fantastic survey of the research on the conditions under which we can and cannot trust our intuitive judgments is provided by Daniel Kahneman's Thinking Fast and Slow, a book that I highly recommend. A related question to when we can trust intuitive judgment is when we can trust expert judgment on complex topics such as politics. And the answer is largely the same. We can trust judgment insofar as it's formed by a process that allows repeated, clear feedback. That is, processes that tell us repeatedly when we are wrong. In the political domain, the resounding result can be characterized with the refrain that political pundits are as accurate as blindfolded, dart-throwing chimpanzees. That is, their predictions are typically not much better than chance, and sometimes worse than chance. Here, I am not trying to be mean to the particular political pundit I've picked. This is Tyler Cohen from the blog Marginal Revolution, who I actually very much like. But the result is rather striking, and it has been demonstrated over and over again in studies involving thousands of high-level pundits who are essentially put into conditions in which they must make predictions that are clear enough for them to actually be wrong. This involves forcing them to make their predictions have a definite timeline for when they're going to be evaluated, so they cannot pull moves like they typically do in their punditry, like saying, even though my prediction didn't turn out, it will turn out sometime in the future, and then not specify when. And make them commit to particular evaluations of their prediction, so that they cannot say, but what I really meant was, or when I said maybe or possibly what I meant was, and essentially to change their prediction so that it's right no matter what. When they are made to submit to having clear predictions, they are shown to do really extraordinarily poorly. And indeed, they're shown to do no better than the average reader of their magazines. But throughout this research performed over 2 decades, it was not the case that all pundits did equally poorly. Indeed, some did somewhat better than chance, and some did somewhat worse than chance. And as researchers, in particular Philip Tetlock and colleagues, pored over the data to try to find the best predictors of better and worse performance, 2 clusters of traits were identified as having the strongest influence on the performance of these political pundits. And these clusters of traits were called the fox and the hedgehog traits. This breakdown was drawn from a poem by a Greek poet, Archilochus, in which, in passing, it was said, "A fox knows many things, but a hedgehog knows one important thing." And this captures something essential about those two clusters of traits. Roughly, the traits of the fox that predict better forecasting performance, better prediction, are the belief that the world is complicated, that many perspectives are better than one, and an attitude of lower confidence in their ability to predict this complicated world. The hedgehog, in contrast, believes that the world is simpler, that one theory explains everything. This might be that everything is explained by class struggle or ethnic conflict or by market behavior. And hedgehogs tend to be characteristically more confident than foxes. Indeed, to drive the difference home, as hedgehogs learn more information, gather more data, their predictions actually become less accurate. That is, in the areas in which they develop putative expertise, they become worse predictors. Whereas foxes, who are willing to take multiple sides, rather than having the data essentially conform to their pre-existing simple theory, will actually improve in their predictions, however marginally, as they get more data. Unfortunately, hedgehogs also tend to be better at promoting their ideas, and this should perhaps be expected. There is something compelling about a simple story of the world told with conviction. All of this together gives us a negative picture as to the performance of intuitive and expert judgment in domains that exhibit complexity. In this graph, we see a plot of the individual's performance in forecasts over the many years of study by Tetlock and colleagues. Across the x-axis, we have calibration, which is intuitively a notion of correct level of confidence. And along the y-axis, we have discrimination, which is intuitively a measure of accuracy, of closeness to the truth of predictions. And what I want you to observe is that we have the mindless competition, meaning the random algorithms, performing actually relatively well compared to all of the pundits. The foxes performing best of all, the hedgehogs performing significantly worse, and the simplest mathematical models that we could make and apply predictively in such situations. These are simple linear extrapolation or regression models, outperforming dramatically all of the participants involved in the studies. For fun, you might notice in the lower left-hand corner the group of Berkeley undergraduates that were also studied, who performed somewhat dramatically worse than chance. For a deeper dive into this body of literature that surveys the conditions under which we can and cannot trust expert judgment, I would point you to Philip Tetlock's excellent expert political judgment. Now that we have the negative picture, we want the positive picture. And indeed, we can do better. It's possible to overcome our biases, calibrate our confidence, and increase our accuracy even in predicting complex phenomena. Our example will be drawn from the book Super Forecasting by Philip Tetlock and Dan Gardner, which documents a series of studies that came from forecasting tournaments in which amateurs were recruited to provide probabilistic forecasts for complex events in politics, international relations, and medicine. And the very best amateur forecasters managed to outperform even US intelligence analysts for every year that the tournament was conducted. So how do we become less wrong? This is what we have yet to learn, but we will see that producing progressively more accurate forecasts, even for complex phenomena, will involve making clear predictions, those that are sufficiently clear for us to tell when we're wrong, and making many of them, so that we can get more clear, repeated feedback. And correcting for common cognitive biases in inductive reasoning, which will be the subject of a future lecture. And finally, in using Bayesian inference, with which we've become acquainted, as a model of rational learning to guide us. In summary, we've seen the negative picture, in which we have a body of scientific literature demonstrating ways in which we're both seriously overconfident and bad at predicting things that are deeply important to us. And we have a positive picture with which we'll become more acquainted that shows us how we can do better, that it's possible to overcome biases, calibrate confidence, increase accuracy, even for challenging problems. Our path, then, from the negative to the positive pictures involves learning the ways that we're wrong, that is, understanding our cognitive biases and trying to correct for them. Learning how to be wrong, that is, making our predictions clear enough so that we can get feedback from them. And learning how to learn, that is, understanding the inductive logic, and in particular, Bayesian inference that can provide a model for our reasoning and learning. The aim of the forecasting project, then, is to practice applying these correctives along with the principles of probabilistic and Bayesian reasoning to real-world problems. Our first step along this path is to make predictions that are clear enough that we can be wrong. Being clear enough to be wrong consists in giving clear conditions for the resolution of the forecast or prediction. Specifically, when will the prediction be evaluated? What will count as being right, as being wrong? These avoid problems such as when one predicts that inflation will rise, we can say if it didn't happen next quarter or next year, it'll happen at some point in the future. We eliminate that by giving a precise timeline in which our prediction must come true. Or when we say inflation will rise, we neglect to say how much, and so we accept a very small increase or a very large increase as being just the same. And saying exactly what counts as inflation will increase beforehand avoids this problem. And what measure and what standard we'll use to determine it. The example questions that we as a class will forecast are the following. 1. How many infections of SARS-CoV-2 will be estimated to have occurred worldwide before 2021? 2. When will the Dow Jones Industrial Average set a new all-time record high? And 3. Will a TikTok user hit 100 million followers by the end of 2020? Your first assignment for the forecasting project will be to give probabilities, your predictions for each of these forecasts. So let's take the first one as an example of how we do this. This was, how many infections of SARS-CoV-2 will be estimated to have occurred worldwide before 2021? With the options less than 50 million, between 50 and 100 million, between 100 and 200 million, or over 200 million. For this first round, I just want you to apply any predictions. You don't need to do research. You can just make your best guess based on intuitions or your existing knowledge. Here, I don't know much about this topic yet, I can imagine, and so I might say less than 50 million seems low, perhaps. I'm imagining that globally there are many countries, there are still many cases to be had, and we expect in the developing world for there to be many more cases. Maybe I think that less than 50 million is relatively unlikely, but I recognize that I don't know that much, so I'll apply 10% probability there. And I look at the other options between 50 and 100, 100 and 200, and over 200, and maybe I think I'm not that confident about the differences between them, and so I might provide initial guess that puts equal probability on each, 30%, 30%, and 30%. Though I might also reason that between 50 and 100 million is a smaller range than between 100 and 200 million, so perhaps I should have put a little bit less in that smaller range. And over 200 million perhaps is, in a sense, the largest range. So maybe I should have put more, but maybe over 200 million is beginning to sound implausible to me. In any case, I will start with my initial guesses, and this will be sufficient, because we will have time to learn more and update our guesses in the next steps of the project. But also it's important that we look at the resolution conditions to get a feel for what a clearly defined question of this sort or proposition of this sort looks like. Here, the resolution conditions are that on January 1st of 2021, we can review the scientific estimates published over the year 2020, and in particular at the end of 2020, of the cumulative total amount of human infections that occurred before the end of 2020. And we'll resolve the question on the basis of the median estimate of the studies published in peer-reviewed journals. This gives us our clear time, January 1st, and our clear criterion, the median of the estimates of those provided in peer-reviewed journals. Our roadmap then is as follows. This week, week 3, we just start with guesses, assign probabilities between 0 and 1 for each proposition. Next week, we'll do some research, and as we learn about biases, we'll think about how to correct for them in our estimates, and then we'll update our estimates given the research that we've done and perhaps some of the methods that we've learned for correcting for our biases. And finally, in the final week, we'll gather yet more evidence, apply directly some of the principles of inductive logic that we've learned, update our beliefs, and write a report that essentially details each step of how we made estimates, how we gathered data, how we corrected for biases, and how we applied inductive logic to learn more. And each of this will do your own version in which you write a report. Importantly then, you'll want to document your guesses for each this week, next week, and in the final week. This then is our forecasting project. I look forward to seeing you in the next lecture. Be well.